The study of galaxies like Andromeda goes beyond mere astronomical curiosity. It holds profound implications for our understanding of the universe's structure, evolution, and our place within it. Andromeda, also known as M31, serves as a galactic neighbor to our Milky Way, residing at a distance of approximately 2.537 million light-years from Earth. This relative proximity makes Andromeda an ideal target for detailed observational studies that provide insights into the broader processes governing galaxy formation and dynamics. One of the remarkable features of Andromeda is its intricate spiral structure. Observations reveal grand spiral arms extending from a central bulge, each arm adorned with young, hot stars, dust lanes, and regions of intense star formation. This structure contrasts with the Milky Way's barred spiral configuration, showcasing the diversity in galactic architecture and the underlying physical mechanisms at play in different cosmic environments. In addition to its spiral arms, Andromeda exhibits a halo of globular clusters and a vast stellar disk extending hundreds of thousands of light-years across. The globular clusters, densely packed groups of ancient stars, are scattered throughout the galaxy's halo, offering clues about its early formation and subsequent evolutionary history. These clusters are believed to have formed during the galaxy's initial stages, capturing the pristine conditions of the early universe within their stellar populations. Studying Andromeda's globular clusters provides astronomers with a unique window into the galaxy's assembly process. The distribution, ages, and chemical compositions of these clusters offer insights into the conditions prevailing during Andromeda's formative epochs. By analyzing the properties of individual clusters and comparing them with those in the Milky Way, researchers can unravel the similarities and differences in the evolutionary paths of these two prominent galaxies. Another intriguing aspect of Andromeda is its dark matter content. Dark matter, an invisible substance that outweighs ordinary matter by a significant margin, exerts gravitational influence on visible matter within galaxies, including stars and gas. By studying the dynamics of stars within Andromeda, astronomers can infer the presence and distribution of dark matter, which remains one of the most profound mysteries in modern astrophysics. Recent observations using advanced telescopes and computer simulations have suggested that Andromeda's dark matter halo extends far beyond its visible disk, encompassing regions where stellar populations are sparse. This extended halo not only provides clues about the galaxy's mass distribution but also offers insights into the nature of dark matter itself, shedding light on its role in shaping large-scale cosmic structures. Moreover, Andromeda's interaction with its surroundings, including smaller satellite galaxies and the intergalactic medium, plays a crucial role in its evolution over billions of years. Gravitational interactions with these companions have influenced Andromeda's structure, star formation history, and overall morphology. Studying these interactions offers a glimpse into the complex interplay between galaxies within the cosmic web, where mergers, accretion events, and tidal interactions shape their destinies. One notable feature of Andromeda's interaction history is its ongoing gravitational dance with the Milky Way. Both galaxies are on a collision course, with simulations suggesting that they will merge into a single larger galaxy in approximately 4 to 5 billion years. This cosmic collision, while distant in time, underscores the dynamic nature of galaxies and their continuous evolution through mergers and interactions. The impending merger between Andromeda and the Milky Way presents a unique opportunity to study galactic evolution on a grand scale. It will transform the structure and stellar populations of both galaxies, triggering waves of star formation, the redistribution of gas and dust, and the formation of new stellar clusters and structures. Such events are pivotal in shaping the diversity of galaxies observed across the universe and offer insights into the formation of massive elliptical galaxies observed in dense galactic clusters. Furthermore, Andromeda's role as a benchmark for extragalactic studies extends beyond its immediate vicinity. Observations of distant galaxies, quasars, and cosmic microwave background radiation often rely on calibrated measurements derived from Andromeda's properties. Its proximity allows for detailed measurements of fundamental parameters such as distance scales, stellar populations, and cosmic expansion rates, which are essential for refining our understanding of the universe's age, size, and composition. Technological advancements in observational astronomy, such as the development of sensitive detectors, adaptive optics, and space-based telescopes, have revolutionized our ability to study Andromeda in unprecedented detail. Instruments like the Hubble Space Telescope, the Atacama Large Millimeter/Submillimeter Array, ALMA, and upcoming observatories such as the James Webb Space Telescope, JWST, continue to unveil new facets of Andromeda's cosmic story. The JWST, with its enhanced sensitivity and infrared capabilities, promises to delve deeper into Andromeda's stellar populations, dust distribution, and chemical compositions. By studying infrared emissions from regions obscured by dust, astronomers can probe the formation of stars within dense molecular clouds and unravel the complex interplay between star formation and galactic dynamics. In addition to its scientific significance, Andromeda holds a cultural and historical legacy that spans millennia. Ancient astronomers marveled at its celestial presence, documenting its appearance in early star charts and writings. The Persian astronomer Abd al-Rahman al-Sufi in the 10th century described Andromeda as a small cloud among the stars, laying the foundation for its recognition as a distinct celestial object. Throughout history, Andromeda's observation has inspired myths, legends, and philosophical reflections on humanity's place in the cosmos. Its depiction in art, literature, and scientific discourse reflects our enduring fascination with the heavens and our quest to understand the origins and nature of the universe. Today, Andromeda continues to captivate astronomers and the public alike, serving as a testament to the interconnectedness of scientific inquiry and cultural imagination. Our universe, for instance, is the Milky Way, and the closest universe to us is the Andromeda system. We estimate there are around 100 billion systems in the observable universe. The discovery of Andromeda has been instrumental in reshaping how we interpret the universe and our place within it. For example, while our universe is the Milky Way, the closest one to us is Andromeda. This disclosure provided undeniable proof that the universe and the idea of creation do not revolve around Earth, breaking the belief that the Milky Way was the sole system in existence and proposing that we are merely a minuscule part of a vast universe. Our understanding of Andromeda has evolved over the past century, primarily through observations made on Earth. However, with cutting-edge instruments like the James Webb Space Telescope, JWST, now available, our viewpoint has radically changed. Recent data from the JWST has challenged our previous notions about the Andromeda Galaxy, presenting new and significant puzzles to solve. The JWST has provided extraordinary insights into our neighboring galaxy, leaving mainstream researchers astonished. Join us as we explore how the JWST has uncovered surprising new information about the Andromeda Galaxy. The view of the Milky Way has advanced significantly throughout mankind's history, shaped by our growing understanding of the universe. In the past, when our technological capabilities were limited, the Milky Way appeared as a hazy band of light across the night sky, inspiring various interpretations and folklores. It was often seen as a magical and central component in the cosmological beliefs of different cultures. During the 1920s, Edwin Hubble, an American astronomer, made an extraordinary revelation using the 100-inch Hooker telescope at Mount Wilson Observatory. Through observations and analysis, Hubble showed that far clouds beyond the Milky Way were indeed distinct galaxies, each containing billions of stars. One of the nearest of these galaxies was the Andromeda Galaxy, otherwise known as M31. Andromeda has a rich history of observations going back hundreds of years. One of the earliest known records of this celestial object can be traced back to the 10th century, when the Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud in star charts from that period. The significance of these observations lies in the fact that al-Sufi was able to identify this distant celestial entity without the aid of telescopes, relying entirely on his keen vision and observations. Later, in 1612, a more detailed description of the Andromeda Galaxy based on telescopic observations was provided by Simon Marius. His work laid the groundwork for future astronomers to study this massive celestial structure. In 1764, the prestigious French astronomer Charles Messier classified the Andromeda system as M31 in his famous Messier catalogue, erroneously crediting its discovery to Simon Marius, unaware of al-Sufi's prior work. For nearly 100 years after this, Astronomers were collectively trying to learn more about this mysterious system, each adding to the previous discoveries. Before that, Galileo Galilei, the Italian astronomer, fundamentally changed how we interpret the Milky Way in the mid-17th century. Using his newly developed telescope, he made pivotal observations that challenged the prevailing Aristotelian cosmology. He found that the Milky Way was not just a diffuse band of light but rather a vast collection of individual stars, planets, and other celestial objects. Through his observations, he demonstrated that the Milky Way was not at the center of the universe, as previously believed, but rather a vast array of stars dispersed throughout space. In 1750, English astronomer Thomas Wright proposed a new hypothesis in his work, A New Hypothesis or New Theory of the Universe. According to Wright's hypothesis, the Milky Way was not an irregular distribution of stars in space but rather a flat layer of stars. He also suggested that a part of this vast structure was our own solar system. While Wright's theory was a step in the right direction in understanding the structure of the Milky Way, it was still limited by the observational technology available at the time. They still believed that the Milky Way was all there was to it, which, considering the constraints, was not surprising. A significant leap in understanding the nature of the Andromeda Galaxy occurred in 1864, when English astronomer William Huggins made a remarkable observation. He studied the spectrum of Andromeda and noticed that it was different from that of a typical nebula, paving the way for the galaxy to be recognized for what it truly is. Andromeda, as a galaxy, has a mass estimated to be somewhere between 1 and 2 trillion times that of our Sun, a massive celestial structure residing relatively close to us in the vastness of space. Based on all the research conducted up to this point, scientists believe that Andromeda is around 10 billion years old, making it very old in cosmic terms. Its age indicates a long and complex history of formation and evolution. One of the captivating aspects of Andromeda's origin is the theory that it formed through the merging of several smaller protogalaxies. This suggests that over billions of years, smaller cosmic entities gradually came together under the force of gravity to form the magnificent Andromeda Galaxy we see today. Such cosmic mergers are common events in the universe, shaping the formation and structure of galaxies. For a long time, astronomers thought Andromeda was significantly larger than our own Milky Way galaxy. From an observational standpoint, such a mistake could easily be made because we are in our own galaxy, and seeing Andromeda from Earth makes it appear so large that one would easily imagine that nothing could come close to its size. However, galaxies are enormous systems, and their mass is intricately linked to the distribution and movements of stars, gas, dust, and dark matter within them. Pinpointing these attributes precisely is a demanding task that requires complex observational techniques and meticulous analysis. This kind of information requires modern instruments, which is why the truth is becoming apparent now. Recent research has led to a reassessment of these beliefs. New discoveries have prompted scientists to somewhat reduce their estimate of Andromeda's mass while simultaneously increasing the mass attributed to our Milky Way. Thus, the current understanding is that the two massive galaxies are much closer in mass than previously thought. The Andromeda Galaxy's actual dimensions are well established. It is known to extend farther than our own Milky Way, with a grand diameter of around 220,000 light-years. Andromeda surpasses the Milky Way's estimated width of around 100,000 to 175,000 light-years, making it a truly massive celestial entity spanning a vast region of space. This revised perspective also highlights the complexities and challenges of accurately measuring the mass of galaxies. At the core of the Andromeda Galaxy, the extremely massive black hole exerts a tremendously strong gravitational pull on surrounding stars. As these stars orbit around the black hole, they follow curved paths, similar to planets circling the Sun in our solar system. At certain points in their elliptical orbit, stars come closest to the black hole, known as the periastron. At the periastron, the gravitational forces are at their strongest, causing the stars to move at their highest speeds. This clustering of stars around the black hole emits energy as radiation, including visible light and other forms of electromagnetic radiation. The increased concentration of stars and the release of radiation create the brighter point of concentration that astronomers observe in the galaxy's core. The core of the Andromeda Galaxy contains an active galactic nucleus, AGN, a highly energetic region characterized by intense emissions across various frequencies from radio waves to X-rays. AGNs are powered by the presence of a very massive black hole at the galaxy's core. These supermassive black holes are extremely dense regions in space where a tremendous amount of mass is concentrated within a tiny volume. When astronomers observe active galactic nuclei using advanced telescopes like the Hubble Space Telescope, they notice a fascinating phenomenon. One of the most intriguing features of the Andromeda Galaxy is its AGN, which seems to have 2 points of concentration. There are 2 distinct regions where light and other forms of radiation are emitting more strongly than in the surrounding areas. The brightest concentration is the second point of focus, slightly offset from the actual galactic center. Within this region lies the supermassive black hole, estimated to be between 11 to 23 million times the mass of our Sun. Supermassive black holes are believed to be common in the centers of galaxies, including our own Milky Way, and play a crucial role in the formation and dynamics of galaxies. When matter such as gas and stars gets too close to a supermassive black hole, it forms an accretion disk around it. This disk of swirling material heats up and emits intense radiation across various frequencies, making the AGN highly luminous. When astronomers observe the active galactic nucleus of the Andromeda Galaxy, they notice a brighter point of concentration near the central supermassive black hole. This feature results from the unique gravitational interactions between the black hole and the stars in its vicinity. The Andromeda Galaxy also has another truly interesting feature: a wealth of globular clusters. These globular clusters are dense groups of stars that orbit around the galaxy's center, similar to satellites circling a planet. Andromeda is estimated to harbor around 460 of these dense and ancient clusters, each containing thousands to millions of stars that formed around the same time. The large number of globular clusters in Andromeda provides valuable insights into its astronomical history and interactions. In conclusion, the Andromeda Galaxy stands as a beacon of exploration, offering profound insights into the cosmic tapestry that surrounds us. From its spiral arms and globular clusters to its dark matter halo and impending collision with the Milky Way, Andromeda embodies the dynamic processes shaping galaxies across the universe. As technological advancements propel us deeper into the cosmos, our journey of discovery alongside Andromeda promises to unveil new mysteries and enrich our understanding of the universe's evolution and our place within it.